Hello. I think that flat Earth is a dead horse that refuses to stop twitching at this point. In my last video, I got comments from not one but two flat earthers. In fact, they started to argue with each other in the chat for some reason. And with all of the interactions that I've seen all the flat earthers have with everybody else, I'm starting to wonder if the rest of the world is playing chess while they are trying to play Connect 4. As expected in my last video, the entire point of the video was completely lost on them. I'll leave a link to it here, but to quickly summarize what I did in that last video, I used the Theodolite app on two different occasions, standing at various distances to a lamppost. I pointed the Theodolite to the top of the lamppost and got an elevation reading, and then I pointed it down at the base and got a different elevation reading. And then doing a whole bunch of math, I was able to calculate the height of that lamppost. Since I did not feel like bringing a measuring tape with me on every single occasion to get a direct measurement reading from the lamppost to each of these observation points, I relied on the phone's ability to calculate and display my geocoordinates. And then with those geocoordinates, I was able to calculate the distance between each of these points using the Haversine formula. And then at that point, it was just simply a matter of using a triangle calculator to calculate the lengths of these other two sides. And mainly, once I had the length of this side and this angle, I was then able to calculate the height above my local horizontal to the top, and then the same thing from my local horizontal to the base, and then adding the two, I was able to get the full height. One of the two flat earthers even told me that the Haversine formula is the correct formula to calculate the distance between 2 points on a flat earth. Since neither of these two flat earthers were able to tell me specifically what I did wrong or where I did anything wrong, I will assume that they are agreeing with the math that I presented. Before I continue with that, I will just generalize the problem this way. The manufacturer of the Theodolite app that I have states the smartphone uses the built-in gyroscope and accelerometer hardware in order to measure the horizontal and elevation angles. The problem is that the accelerometer does not measure horizontal. The reference angle of an accelerometer is the down direction, or in other words, the direction of gravity. The phone's natural orientation direction is vertical because it is tied to the direction of gravity, and horizontal being a 90-degree angle from vertical means that the phone is converting a zenith angle to a horizontal angle, and it is displaying that horizontal angle. So if I'm pointing the phone at a lamppost, my phone has absolutely no clue where my horizontal eye level is on that lamppost. The only thing it can do is produce an elevation angle relative to the direction of gravity, which is the complementary angle of the zenith angle. I did also state indirectly in my last video that being hastily done, I did not take into account at all any change in elevation angle between two different points. And it was quite clear in one of the graphs that the ground was uneven. I knew ahead of time that that was completely irrelevant for that specific exercise because I was trying to measure the height of the lamppost above and also below my eye level. So if I was standing an extra foot higher here, this angle would have been less and this angle down here would have been more, but the sum of those two lamppost sections would have been the same. So this is ultimately the problem that flat earthers continually refuse to address. Ignoring atmospheric refraction and also ignoring the fact for a moment that Polaris is not at 90 degrees declination but is 89.25 degrees of declination, the general rule of thumb is that the elevation angle to Polaris will match your latitude. Flat earthers also seem to accept 60 nautical miles per degree rule, which converted to kilometers is 111. And so with that, I use the same triangle calculator formulas that I showed in my last video in this one, starting directly at the North Pole all the way to the equator at a ½ degree latitude delta. The distance in kilometers between those two latitudes happens to be half of that. If we accept the general rule of thumb that the elevation angle to Polaris matches your latitude, then between, let's say, 89 and 88.5 degrees latitude, two of the angles of the triangle are known. The third is going to be obviously 180 degrees minus the other two. Knowing the length of one of the sides, we can calculate the other two sides. Once we have the hypotenuse, once again, if the Earth was flat, and I am computing the consequences of the flat Earth hypothesis, we should be able to calculate the height above the North Pole for Polaris using the length of the hypotenuse from the observer at a given latitude and the corresponding elevation angle to Polaris. I'm going to make this spreadsheet available. Once again, if flat earthers doubt that, they can look at the math, but I really doubt that they will. And you can see very clearly that as you approach the equator, if Polaris was a single object that everybody was looking at, that at the equator, Polaris would have to be directly on the ground. Here's a nice little chart that I made. Just like so many people have asked flat earthers before, how high is Polaris? I'd like to go back to the other comment that TB-XX-whatever said, which is that the Haversine formula is the correct formula to use to calculate the distance between 2 points on a flat Earth. So if the Earth is flat, and if the Haversine formula is the correct formula to calculate the distance between those 2 points, in this tab, I'm using the Haversine formula. Starting at 89 degrees latitude and longitude of 0, I keep adding a ½ degree of longitude until I get to 2 degrees, and then after 2 degrees, I subtract a ½ degree from the latitude and go back to ½ degree separation of longitude, and I keep repeating until I get to 89 degrees south. So if the Haversine formula is the correct formula to calculate the distance between two geocoordinates on a flat Earth, how does the distance at different latitudes compare? And that's what it looks like. This one would be ½ degree difference in longitude. This one would be 1 degree difference longitude. That there is about 111 kilometers. That's about 222 kilometers, which is 2 degrees. That does not look at all linear, which is how it should be if the Earth was flat. So in this tab, I'm using flat Earth math. These are the same geocoordinates that I used in the last one, the same formulas, the same algorithm that I used to generate these geocoordinates. If I were to plot these geocoordinates on a Cartesian map, longitude of 0 would be on the x-axis to the right. So I'm using the cosine of the longitude multiplied by the distance to the North Pole, which is again 111 kilometers per degree in latitude degrees. Y is the same as x, except it's sine rather than cosine. X2 operates on these two rather than on these two. Then I calculate the length of the hypotenuse by taking the square root of the sum of the square of the other two sides, and I get this distance here. And it looks straight and linear as one would expect. And I wonder where I saw those two before.